consider this node here where the inductor and the capacitor and the load are connected. Now, according to Kirchhoff's current law, the current flowing towards this junction equals the current flowing away from the junction. So that means IL is equal to I out plus IC. But if we consider that the charge on the capacitor Q is equal to CV is equal to IT, then since the voltage over the capacitor at the beginning of each cycle is the same as at the end of the cycle, since V out is a constant, that means that the current flowing into the capacitor multiplied by the time that the current is flowing into the capacitor, it must be equal to the product of the time when the current is flowing out of the capacitor and the time that it is flowing out of the capacitor. So the charge Q on the capacitor is a constant. That means that just as much charge is flowing into the capacitor as it is going out of the capacitor in a period. That leaves us with the following conclusion, that the average current flowing through the inductor is equal to the average current flowing into the load. Now, the average current flowing into the load is the DC current, and it is I out. Therefore, the average of the inductor current must be equal to I out. Furthermore, we can also say that the average current flowing out of the battery or the supply here is equal to the average current flowing into the load. We are looking at ideal conditions here. We haven't taken any losses into consideration in order for us to understand the operation of this buck regulator. So here I have the average, or I have the inductor current, continuous conduction mode, and I can determine the average current through the inductor, and I've put it down here as I out. Now, I out is equal to the area underneath the graph here divided by the period. And since this is a triangle, I know that the area divided by the period of the inductor current, I know that the area is equal to a half base times perpendicular height of that triangle and divided by the period, which is t. So this half base, or the base here is t, so therefore it is equal to a half times t, and the perpendicular height is IP. This t goes into that t once, and therefore I can say that I out is equal to the peak current through the inductor divided by 2. So now I have I out, I have the ratio between I out and IL, and the peak of IL. Now what about IC? If I want to determine a graph for the capacitor current, then I see that IC is equal to IL minus I out. So if I subtract that value from this triangle, then I will have IC. So at that point there, I will subtract the same value from each other and at that point there. So therefore, those 2 points must be 0. At this point here, I out is a half of IP, so then at that point there, I must have I peak over 2, and at this point here, at this point here, I must have I peak over 2 minus 0, so I will have I peak over minus I peak over 2. So now I can sketch the current IC. So where is the capacitor charging? Well, during this period here, the current is positive, so there the cap is charging. And during this here, the cap is discharging. Since the current is negative. That area there, the negative area here, and the positive area must equal each other in order for the voltage over the cap not to increase or decrease over a time. Now let's look at this R. This R usually represents the load. Now the load is not necessarily resistive, but in order for us to determine an equivalent resistance that will give us the same conditions, we can say that R equivalent is equal to V out divided by I out. Now what would happen if R equivalent is suddenly halved? What would happen to the inductor current here? Well, if the R equivalent suddenly becomes half of what it was, then it means that since V out is constant, it means that I out must have doubled. So this I out would move up to that point there. So I'm just first going to redraw this as it was here and have an I out there. And remember now what we said. The duty cycle does not change. The output voltage stays the same. So it means you cannot go and change the slope of this current here in order to accommodate double I out. So I'm now going to sketch 2 times that I out there. So we're now at 2. That's horrible. So we must maintain this slope, and that just means that in order for us to have a double I out there, we now will have a wave shape that looks like that, and that will be our new I peak. And the I out will now be there. Well, R equivalent is now divided by 2. The voltage over the inductor will stay exactly the same as it was before. Thank you.